Hello, beautiful calculus people. Welcome to your Friday pre-recorded lesson. We are going to take a look at the limit definition of the definite integral, which is going to harken us back to looking at the limit definition of the derivative. So it turns out that thinking about a definite integral is very similar to approaching this integral with respect to certain limits. So we want to make that connection, and now that we've seen a little bit of summation theory, so working a little bit with those infinite sums, it's really not too challenging to make that connection now. So now feels like the appropriate time to give a little introduction to this. And the reason I'm doing this a little bit later is because, one, I wanted to do that little bit of introduction to working with sums first, and two, it gives us a little excuse to go back and do a little bit of review at the same time. So before we kind of hand-waved a little bit, I said use your intuition. The idea is to work with these rectangles, and we're going to add them up, and we're going to let the integral kind of represent the sum of those rectangles. Now, that idea is really the same idea that we want to use here, right? So the idea doesn't change. The idea is still the same. It's just how we set up and process that idea that's a little bit different than kind of the hand waviness that happened a little bit earlier. So let's redraw that picture, kind of refresh our memory on what that sum of rectangles actually looks like. So what we're going to do is we're going to draw some kind of function. Let's call it f of x. And we're going to pick some endpoints. So this is the definite integral. So in other words, we're going to have an endpoint called x is equal to a, and an upper endpoint called x is equal to b. So these, as you know, are going to become the bounds of integration for us. And we're going to have a series of rectangles inside of the boundary numbers here. I'm maybe going to draw just a couple and somewhere here in the middle, but we would have n of these rectangles inside of our interval. Okay, so maybe here's one rectangle in green, here's another one, and we'll have one up here. So we'll do 3 rectangles. And what we're going to do is we're going to look at this middle rectangle. Okay, and you can assume that these rectangles are going to go off in either direction. So maybe I'll just stay with green. Let's talk about the width of one of these subintervals. We said that the width of one of these subintervals, we've usually called this delta x, because this is a small change in the xward direction. And then one thing that might be helpful is up at the top here, we can also label this point on the curve f of x. So let's say I don't really know exactly the x value here, so I'm going to be calling it xi. And it'll become a little bit more clear kind of what these xi's are as we work through some number examples. But we're going to pretend here that down here along the x-axis, we've hit some kind of x number, and I'm going to input that x number into the function to figure out how high this function is at this particular x number. So inputting that number in, we're going to get f at xi. That's going to be our y value, right? So as I kind of scroll over here is going to be our f at xi. So remember that kind of the idea here is that all of these rectangles have a width of delta x, And then provided we know where the x value is along the x-axis, I can evaluate the height of these rectangles, and they all come out being f of x high. But f of x, of course, depends on our value that we've chosen along the x-axis. Okay, so let's see. Do I need that? Is that important? Okay, so a little summary. So actually, each rectangle is going to have an area that's equal to. So the area of each rectangle should be the width times the length, or the width times the height. We know that the width is delta x, and the height is going to be given as f at whatever the x value is that we're working with. So we call this f at xi. Now we could do a little bit better with our delta x. We could actually calculate roughly how wide these subintervals are by performing the following calculation. So we could take the difference between b and a, so that gives me the length or the distance from a to b, and then we could divide by how many rectangles are going to be put into this interval from a to b. Okay, so b minus a here represents the distance from a to b. And n is going to represent the number of rectangles that we would like to put in between a and b. Right, so in other words, the width is dependent on our choice of endpoints, and it's also dependent on how many rectangles we would like to put into this particular interval. But that's a general summary. We have area as delta x times f at xi star, with the width given by the following formula. And so what we could do is we could essentially express, the area roughly as the sum of these rectangles. And I should say the net area. Because if f of x is below the x-axis, the area, the calculation that we get here may not necessarily come out to be a positive number. So we have to be careful. I'm going to use the phrase net area here to describe that region. It's a signed kind of area. But the net area bounded between f of x and the x-axis, essentially we can now express it as a sum. Okay, so our net area is the sum of a bunch of different rectangles of height xi star and width delta x. And I is going to range from 1 to n. So our index is going to range through the number of rectangles that we have. So in other words, we want to have an upper bound that's n, because for this particular area we have n rectangles that we're using to approximate the area underneath the net area between the x-axis and f of x. So that's the big idea. And maybe I'm just going to pull that down just a little bit so it's a little bit away from that little caret that I have. And then we just try to connect it back to this idea that we had talked about before. As the width, as delta x starts to get smaller and smaller, or alternatively we could say as n starts to get very large, so as the number of rectangles increases, we will eventually start getting closer and closer to the actual area, the net area that's bounded between the x-axis and f of x. So that's the last little bit of the idea of the definition here, is I have a approximate formula using summation notation, and the last step is just to allow the number of rectangles to tend towards infinity. So this is where the limit part of the definition comes in. Okay, so here is our full definition of the definite integral. So if we have a function that is defined on a closed interval between x equals a and x equals b, we can define the definite integral in the following way. We basically say that the integral from a to b of our function with the differential dx is defined to be the limit, as n gets really big, of the sum of the rectangles that approximate the area. Now within this definition, we might want to just let the reader know what delta x is, so we're going to put that in here. Now the formula for delta x doesn't change. It's always b minus a over n. So it's always dependent on the number of rectangles that we have if we're just approximating our integral. But if we let the limit of n tend towards infinity, then we actually legitimately get the definite integral here with the bounds. And another thing we can do inside the definition here is to let the reader know how to calculate xi. So how to calculate the different x values that we're going to be substituting into our function. So xi is generally given using the following formula. It's given as a plus I times delta x. And let's see here. I is going to start at, well, I have to be a little careful here. I could start at different values, but this is the generalized formula for xi. So I could either start at 0 or I could start at 1, and we'll talk about the different cases that could happen. But this is the important definition that I need you guys to know. So if you're ever asked, there's going to be one question, I think, on the final exam where we have to utilize the limit definition to do some stuff. And this is what we're going to be using. We're going to be using a limit of a sum with a couple of extra formulas here at the bottom in order to do the work for us. And I do have a little note in my personal notes, and that is we're going to see a couple of different cases where we have some flexibility on choosing the xi number. So if we scroll like back up here to our photo, I was taking xi to be at the like the right hand side of these intervals. You can see that like my next xi would be here, and then my next xi would be here. So all of my xi's kind of lined up along the right side of these rectangles. We don't have to do that. The textbook will go through this a more generalized procedure for you. We're going to use a couple of different cases. We're going to use xi's that happen on the right-hand side. We'll see a couple examples of xi's that happen on the left-hand side. And then I'm hoping that we'll do an example or two of xi's that happen right in the middle of the interval as well. But technically, the x values that we choose can really be anywhere. Like, you know, as soon as I set up my rectangle, they could be anywhere inside of that dx, that delta x region. It doesn't really matter where we choose our xi, because the widths get smaller and smaller. So because those widths get smaller and smaller, all of the xi's essentially get kind of pushed towards one x value anyway. So in the long run, it doesn't really matter. In fact, I believe you can even probably set these things up so that the rectangles aren't even, like, the widths don't even have to be the same size. So there's ways we can generalize this, but it's not helpful in practice typically to do these kind of like awkward things. But the textbook will talk about that. So I had made a note just to let you guys know that it's possible to take different widths. It's possible to take different x values inside of that little delta x region, and everything is fine. Everything works out completely fine because we're taking that limit, right? As the limit, as n gets really, really big, that limit pushes everything towards the same kind of x number. But realistically, what do you guys need to be able to do? We need to be able to utilize this definition to be able to prove that an integral actually equates to what it is. So there will be an example that's going to look something like this on the final exam. It's going to say, use the limit definition to do some stuff. And so what we're going to do is we're going to calculate the definite integral of x plus x squared between 1 and 3. And we're going to do that using the limit definition. Now, typically, I break this down into two major steps. The first step, when I know that I have to use the limit definition, so this is really the key here. I mean, if it says use the limit definition, we have to go back to this definition up here, and we have to try to evaluate using a sum of rectangles, okay? A limit of a sum of rectangles. So there's no way around this. We're going to have to use the limit definition to do this. The first thing we want to do is actually utilize some of the formulas down here, because when I go to write my integral in terms of the summation, it'd be nice to know what these two things actually look like. Right now, they're just very algebraic, but I'd like to get some maybe numbers in here and see what they look like. So that's generally step number one. Step number one is generally going to be, okay, what does delta x equal? Well, we know delta x is b minus a over n. Now, n we don't know because n is going to be tending towards infinity. So n should really be the only, well, n and I are going to be the only parameters that we have in these formulas. But we do know that b and a are given over here. So this is a, this is b. So we can put b and a in. This is going to be 3 minus 1 over n. So delta x is 2 over n. So that's the size of each of these little subintervals along the x-axis. Each of those subintervals is going to be 2 over n big. And of course, as we let n tend towards infinity, these start to get smaller and smaller and smaller. The other thing that might be helpful before we even think about the formula of converting the integral to the summation notation is, let's think about what xi is going to look like. And xi is given by the formula a plus I delta x. Okay, so in other words, if I'm looking at the x-axis and I know I'm on the interval from a to b, the very next x number that I want to pick is a plus a single delta x. And then the next x number I want to pick is a plus 2 delta x's. And I just keep doing that until I land on b. That's the idea with this particular formula. So a, you can kind of think about this as like a plus 0 delta x's, if that makes sense. And each of these widths is delta x, right? So we're just adding a bunch of widths along the way. And that's the idea here. So I'm going to erase that just because I'm going to need this space. So if you need that, just kind of pause the video, go back, copy that down. That might be something that would be a nice visual for you guys to know. So xi, let's see, we know a is 1. I don't know what I is going to be at the moment, so let's just keep that as I. We do know what delta x is. Delta x is 2 over n. So xi is 1 plus 2i over n. now that I've used the preliminary formulas to find delta x and to find the x values that I need along the x-axis, we're going to ask ourselves, what is the function that we're actually working with here? And if I were to sub in these x numbers that we call xi, what are going to be the outputs, right? So what does f at xi, f evaluated at xi, actually look like? So f of x is given inside here, right? So if we kind of scroll back to the definition, f of x is that thing that's given inside the integrand of our integral. Okay, so f of x is going to be x plus x squared. That means f at xi is going to be xi plus xi squared. And I know what xi looks like. Xi is 1 plus 2i over n. So let's go ahead and input that down here. So this becomes 1 plus 2i over n plus 1 plus 2i over n squared. So xi plus xi squared. This is kind of annoying. They don't always come out to be this annoying, but we are going to have to expand. Well, we don't have to right now, but my suggestion is to expand this squared business out just to make it look a little bit nicer. And potentially we can simplify some stuff as well. So I'm going to expand this perfect square out. We're going to get 1 plus 4i over n plus 4i squared over n squared. So if you need to, take a moment to expand that, right? If you need to, just write it out. And show that you get exactly these three terms when you add everything together. Now, it looks like I can simplify a little bit more. I can add these things and I can add these things together. This one's going to be kind of stuck by itself because there's an I squared and an n squared. So we end up getting something simplified that looks like this. So the heights of all of my approximating rectangles are going to be 1 plus 1, which is 2. 2i plus 4i over n, so 6i over n. And then we're going to have this leftover 4i squared over n squared. So that's pretty much as good as f at xi is going to get. And that's what I would consider to be kind of the second step in utilizing the definition. Our third and final step is the annoying part, which is to put it all together. So the formula says the integral that we start with should be equal to the limit of a sum of approximating rectangles. So let's start with the integral we have. We have the integral from 1 to 3 of, I think it was x plus x squared. Okay, and this should be equal to the limit, as n goes to infinity, of a sum of approximating rectangles, where f at xi star is, f at xi is given as 2 plus 6i over n plus 4i squared over n. Okay, so I'm taking this expression and putting it in here. And we have to scroll back a little bit to get delta x, but delta x is given back here. Delta x is 2 over n. That's what I'm going to be putting in right here. So that's the substitution step. And now we have the capacity to actually go through the process of simplifying this to see what kind of numerical answer we get. So we should be able to fully simplify this. This is a limit and a sum that's not an infinite kind of sum. We have formulas to deal with a lot of this stuff. So f fasten your seatbelts. I will try to not use a highlighter to write out stuff so that we can see what the hell's going on. First and foremost, we have to deal with I first. We have to deal with this sum first. So that's what we're going to be doing first. We want to deal with sum first. So I'm going to distribute this 2 over n through the brackets, and then try to distribute the sum as well, because we have an addition of finite objects. So I'm going to write down the sum again, and I'm going to distribute this 2n through the brackets so that we get 4 over n. We get 6 times 2, which is 12i over n squared. 2 times 4 is 8, so 8i squared over n. It should be n cubed. I think I wrote something down wrong here. It should be n squared, so just make that fix there. If you need to, this should be n cubed. And you're going to see I'm not a math robot, despite what some people might say. It's very easy in the limit definition to make a small algebraic error like this, so you'd have to be really, really careful with stuff. Okay, again, putting this limit aside, let's deal with just the sums first. So what do we get here? We're gonna, when we distribute the sum through the brackets, and we can do this because there's addition that's separating all of our stuff, we get the sum of 4 over n. We get the sum of 12i over n squared, and we get the sum of 8i squared over n cubed. Now what we would like to do is we would like to refer back to a couple of the formulas that we saw in the series lesson, and I'm just going to recall them back into our memory. They should be closer to, they were before geometric series, so a little bit closer to the start, I think. Yes, so these nice formulas to know. So these are the formulas that we're going to be able to utilize right now. The sum of a number is just n times that number. The sum of the first n numbers is n plus 1 over 2. The sum of the first n square numbers is n plus 1, 2n plus 1 over 6. And the sum of the first n cubed numbers is n squared, n plus 1 squared over 4. So those 4 formulas we're going to start utilizing right away. So if you need to, pull them out as a reference. And I'm going to bounce back into the limit definition here. And I'm going to just try to rewrite this in a way that allows us to utilize the formula. So this is probably as good as it gets. You'll notice that you can probably skip a couple of these intermediate steps once you start to see the pattern, but these terms here, I can factor these terms out. Because there aren't any i's in it, I can think about these as like a constant times I. So I can factor this 12 over n squared, I can factor out this 8 over n cubed. That's totally fine because those things don't depend on the index, and the index here is I. And so what I've done is I've essentially now converted like this or starting thing into something that I know the formula for. This is the sum of the first n whole numbers, which is n plus 1 over 2. And the same thing happens over here. I've converted the original thing into the sum of the first n squared numbers, which is n plus 1, 2n plus 1 over 6. So we're going to go ahead, we're going to pull those formulas in order to simplify these two particular sums. And then the last one we have to deal with over here, we have essentially 4 over n. 4 over n is a constant number from the point of view of this summation because the summation depends on I. So what we're going to get here is we're going to get n times 4 over n. We're going to get n copies of 4 over n. So let's go ahead, I'm going to write this all in if you need to, pause the video and just take a hot second to bask in the craziness that is the limit definition of the derivative. Okay, so like I said, this is a good time to pause, make sure that you understand the process of dealing with the summations. We deal with the summations first, and now because we've dealt with all of the indices I, we can now start simplifying these fractions and working towards figuring out how to evaluate this limit. And what you are going to notice is that this particular step, it is going to be possible maybe to cancel out some numbers or cancel out some of the n's, which is what I'm going to do next. So in red, I'm going to go through, we're going to cancel out, say, this n. Those n's are obviously going to cancel. 12 divided by 2 is 6. And we can certainly get rid of one of these copies of n because we're factored over here. Dividing by 2, 8 over 6, so let's divide by 2, that would be 4 and 3. And again, I should be able to get rid of one copy of n here because those will divide and give us 1. So let's go ahead and rewrite out the simplified form here, and then we're going to eventually distribute this limit to each of these fractions in hopes that we can simplify this a little bit. So inside our brackets, we get 4 plus, let's maybe factor this through, 6n plus 6 over n. And same over here, I'm going to factor out the black terms here. So 2n squared plus n plus 2n plus 1 over 3n squared. I'm going to do a couple steps in this next line. I'm just going to distribute the 4 through the brackets here. And I'm also going to be distributing the limit to each of these terms as well. So we're going to get limit as n approaches infinity of 4 plus the limit as n approaches infinity of this fraction plus the limit as n approaches infinity of this fraction. We should get 8n squared. This is 3n times 4, so I believe that's 12 n's altogether, and a 4, and 3n squared. Beautiful. So the limit says we can essentially just deal with each one of these things one by one. Obviously, the limit of 4 is 4 by L'Hopital's rule, so we can kind of consider L'Hopital's rule looking at the leading terms. The leading terms are 6n and n. This is going to boil down to the number 6. And of course, you're looking at the leading terms, which are the highest powered terms, 8n squared and 3n squared. Dividing out the n squareds, we're going to get 8 over 3. Okay, so that's either looking at leading terms, like I told you guys in Calc 1. If you weren't with me in Calc 1, maybe you guys would have done L'Hopital's rule. Just go through L'Hopital's rule once or twice, and then these limits are going to pop out as 6 or 8 over 3. But they should always come out to be the ratio of the highest powered terms in the numerator and denominator. So what do we get here? We get 10 plus 8 thirds, and let's just simplify that. 10 is what? 30 thirds plus 8 more, so we should get 38 over 3. So that's our final answer. That's going to be what this integral is using the limit definition of the definite integral. Now, you're probably going to be like, why in the hell are we doing this? And I'm going to agree with you, because we already know the fundamental theorem of calculus. And the fundamental theorem of calculus says, oh, why don't you just find an antiderivative and evaluate it at the endpoints of 3 and 1? That's what the fundamental theorem says. It's much faster, right? It's a lot faster, which is why my focus for this course has been looking at the fundamental theorem and utilizing the fundamental theorem to do a lot of work with us. Because I agree, I think it's just much faster to be able to utilize the fundamental theorem. 3 times 3 times 3 is 27. And just use the fundamental theorem to do these calculations. It's just much easier. So I'm not going to the point here is not to argue with you. The point here is to show you where the theory came from. So before we had the fundamental theorem of calculus, we were kind of stuck, right? We were kind of stuck doing stuff using limits in the long way by hand before we really had bridged that connection to the fundamental theorem of calculus. But a quick double check here, just by using the fundamental theorem should verify that our final answer of 38 over 3 is right. So I ended up kind of simplifying this to 4 plus 26 over 3. 4 is 12 thirds. And I keep writing 3 for some reason. And I believe 12 and 26, that should give us our 38 that we're looking for. So you can usually verify that your calculation is correct by using your calculator or just doing this by hand, which is totally fine. And if I scroll it, you can kind of see how annoying it is to do it the long way versus using the fundamental theorem. But at the end of the day, there are some integrals that are going to be just way too hard for us to actually evaluate utilizing the fundamental theorem. So I guess the goal eventually of this lesson is to develop these techniques, which we're looking at right now. This is what we call this will be a right-hand limit technique, using these techniques to understand how to get a number and what that number means. So the number that we ended up getting is true. It's like the true net area, 38 over 3, from using a right limit technique, and we'll talk about what that means probably next week. But yeah, just for now, know that yes, it's obviously 100 times easier just to utilize the fundamental theorem than it is to calculate a limit. I get that, but still, we want you to understand the limit definition just like we did for derivatives. I want you to be able to know how to do one of these questions with the understanding that we don't normally do this in practice, and very rarely do we need to do this anyway. We really only need to do a technique similar to this when we can't integrate something, when we need to approximate the area, when we can't actually find an antiderivative. So I'm just going to quickly check and peek at the time. Yeah, we're about 40 minutes. I think, these tend to take a little bit of extra time. So let's leave it at that for now. And what we'll do on Monday is we'll kind of pick up with this on Monday. We'll do another example of using the limit definition like this, and then we'll start talking about the different kinds of techniques we can use when working with integrals like this. If we have to do this kind of limit technique, there's a couple different ways we can do it. So we can use a right technique, a left technique, or the mid technique. And then there's a couple other kind of specialized approximations we're going to probably talk about next week as well. So awesome. So just remember that you have that quiz due by Friday at midnight, so don't forget about that. Otherwise, I will see all of you on Monday. Have a lovely weekend.